And actually, the neutron stars are much more complicated object. It's not simple as a black hole. The neutron star, you know, no even horizon, so it has matter inside, which we are not well which we are not well tested. They have more high magnetized objects and more compact as compared to the stars, and the mass is in the range from 1 to 2.4 solar masses. But in observations, if we found some neutron star more than this mass range, we can explain this. It's TOV equation. It depends on the matter inside the neutron star. And the density, matter density in the range, this 10 to 11 and 15 gram per centimeter cube. It is very dense, the same in the order of dense of neutrons, and the surface gravity is very. It is almost 10 to power 11 times stronger than the gravity, stronger than the Earth. It is for us it is 10 approximately. You see, it is very strong. So for example, for Crab pulsar in the Crab which is found in the Crab nebular center, it is about 1 solar mass, and the mass and the period is 33 millisecond, mass about the 10 kilometer. Even the gravity is very strong on the surface of the neutron star. We can compare the gravity and the Lorentz forces, which is on the electron. For example, we can easily approximately calculate it is 10 to minus 18 Newton, and for electromagnetic forces it is more than this 10 to 13 times larger than gravity forces for electrons. It is 10 to power 10 billions times larger for protons. It is just estimations. And why so fast the neutron stars and highly magnetized? So it is due to during the collapse, this magnetic flux is conserved, and we can see that from using the conservation of magnetic flux, we can calculate how much time magnetic field of the star will increase, and assume that the star is 10 to billion meter, and the neutron star radius of neutron star at the end of collapse 10 to power 4 meter. It shows that it increases 10 billion times, and if assume that the star collapsing star's magnetic field is 100 Gauss, it will be 10 to power 12 Gausses. And the fast rotation can be explained due to using the conservation of spin angular momentum. And so we can see that if assume a star rotation period is 1 month, so the forming a neutron star from the collapse of the star can be about the 6 milliseconds. So the condition for the stability of the star is so gravity forces can be should be more than centrifugal forces, otherwise the star matter will fly apart around. using this condition, we can estimate the minimum density of the star matter. It shows for the Crab pulsar with the period 33 milliseconds, it should be 1.3 10 to power 11 gram per centimeter cube. We can also estimate using this condition and knowing this minimum radius of the star, and this radius can be for less than 20 kilometer for the parameters of Crab pulsar. So here I divided by two groups as a with the it is the age is not really age of stars. It is some parameter for young stars. For example, Magnetaris. Magnetar is also highly magnetized objects. In fact, they are neutron stars, or maybe in some models, magnetars is explained as the strange stars, which consists of strange quarks. And this object is magnetic field about 10 to power 15, and they are slowly rotating. It is about from 10 seconds. It should be in minutes. It is not. It's 10 from 1 to 10 seconds, and the spin down rate is very high. It is spin down rate. It's very high. It is 10 to minus 11 about. And for millisecond middle-age neutron stars, known as normal pulsars, radio pulsars, can also be in this range. With the range, magnetic field is about 12 and 14 Gausses, and the period of pulses is about 0.1 up to 1 second. And the period delay, this pulse delay with is 10 to the power minus 15. So all pulsars are called millisecond pulsars. Magnetic field is from 10 to the power 8 to 12 Gausses, and they are millisecond from 1 to 100 milliseconds. And their so period derivative is 10 to the power minus about minus 20. So from this point of view, these pulsars known as a very accurate clocks of the universe. You see, during the 10 to the power 20 seconds, they can their pulse slows to 1 second. Okay, so here the distribution of pulsars in the magnetars, isolated neutron stars, and the rotation powered pulsars, and the compact central objects, millisecond pulsars, and the low mass X-ray millisecond pulsars in low mass X-ray binaries. So in this plot, it is magnetic field and period, similar to the PP dot diagram, and we can see this is the number of radio pulsars and the magnetars observed in the in observations, and we can see mostly observed pulsars are radio pulsars, and up to now there are 2,500 more than 2,500 millisecond pulsars observed, and about 50 magnetars are observed, but still energetic source of pulsars are still under question. It's not completely solved problem. So for the first time, the energetic source of millisecond pulsars is suggested by the Pacini and the Gold the same year, and they assume that since neutron stars fast rotating and their kinetic energy transforms to their radiation energy, so the neutron star should be sourced by their kinetic energies. Due to this kinetic energy loss, the pulsar radiate and slows down. Here some more energetic sources pulsars models. For example, this for the first time this rotation pulsars model, and the accretion powered model also suggested in the binary X-ray pulsars, and the magnetically powered model is suggested by Duncan and for magnetars. But in the green, binary X-ray pulsars and the low-might X-ray pulsars powered by the accretion flow, and the millisecond pulsars and the radio pulsars, rotation powered pulsars, and the new model has been suggested by Akhmedov and Morozova, oscillating powered pulsars. And what is the main goal from this? It can be explained. There is some questions, so the pulsar can explain this fast radio burst phenomena and the part-time pulsar phenomena. So we can discuss later this about the mechanism of originating this astrophysical phenomena. So how the fast radio bursts, FRBs, and bursts from neutron stars, and what is the mechanism of the part-time pulsars? Do they work as part-time? So we can try to explain. So the estimation, simple estimations show that this ratio, the energy loss of rate of energy losses from rotational kinetic energy for Crab pulsar is about 10 to the 38. It shows that the 100,000 times larger than the luminosity of solar, but the solar radiate uniformly, so you can observe their radiation everywhere around the solar with the same luminosity, but pulsar radiate very smooth angle, so it is at the laser beam. We can observe at the peaks, and here the similar diagram for different types of neutron stars. For example, these two objects, compact central objects, are can be seen through their high temperature, and recyclic binaries, and the pulsars, and the radio rotation transits transits can be explained at the rotation powered mechanism. So here we show that the pulsar radiation mechanism and the mechanism of this electromagnetic radiation of dipole radiation. So here pulsar is estimated neutron star with the dipolar configuration magnetic field, and this dipole has a inclination angle between the spin of neutron's rotation axis and the dipole axis. And here we can see that the rotation power is proportional to the angle of sine square. So if it means if there is no angle, the dipole radiation does not occur in the pulsars. So this is how the rotation kinetic energy extracts the electromagnetic radiation. And here the simple explanation, simple estimation for the minimum value of magnetic field and maximum value of magnetic field, and this Poynting flux at the energy density of magnetars for Crab pulsar. So it shows that the Crab pulsar should be actually it should be less than. Yeah, it should be less than its type. So it is 4 times, so for 10 to power 14, and its energy density should be 6 times 10 to power 23 per second. We provide some estimations on the Crab pulsar. So what is the characteristic age of pulsars? But it means that how long live pulsar radiating electromagnetic field, and so here I show the simple calculation is the characteristic age of T. So for pulsars actually this PP dot is constant, and on the other hand, we can integrate from P0 up to P, and the P is much actually this is much higher than the P its period. So pulsar slows down, and its period become larger and larger, and the P square become much higher than P0. We can drop this part, and we can easily find this characteristic age using the observational parameters. Actually, what we can observe from their period signal from its peaks and its peak period delay of pulse, second pulse. And as we told that here actually for rotation powered pulsars, should slow down. So it means their period should increase, and the magnetic field does not play a role in the energetic source of neutron stars. It should be constant. And for magnetically powered neutron stars, I mean, so magnetars period should not change, but all radiation come from the magnetic energy. But observations show that this their period increases, pulsar slows down, and the magnetic field decreases. So this, for example, the position of pulsar neutron stars in the PP dot diagram should change the position this for right and the right and the bottom in this diagram. So it means that their magnetic so as they ages, their position should be down, should move to down and to right, because they slows down due to the radiation. So it means from this point of view, so it is not totally agree with the observations this magnetically and the rotation powered models. Maybe here some model where both models work. Here we can test these effects. How we can test? We can measuring by breaking index. So we can easily calculate this breaking index using this spindle for the rotation powered model. The rotation luminosity of radiation come from the energy losses. So the energy loss is, on the other hand, this we calculate the dipolar radiation in this form, and here we can compare these results. We can get this omega dot proportional to omega cubic for rotation powered pulsars. It means that this cube we change then this 3 we can change for number n. It is index, breaking index. For rotation powered pulsars we can see that it is 3. But how about observation? In observations it can be less than 3, so we can say that if it is less than 3, we can say it is not purely rotation powered pulsars. It can be there is another mechanism to provide radiation. So from this point of view, theoretically studies of this breaking index are very important. Here how to calculate this breaking index using this observational data. It's easily shown. It is simple mathematics actually. And how about the inner region of neutron stars? So neutrons, the inner structure of neutron stars. So as we can, some models say that neutron star has uniformly distributed matter inside the neutron star. So the so the density is constant inside, and but some models say that this core of neutron star still unclear, but the crust of neutron stars actually consists of nuclei, mostly this ferrum 26 isotope, and the electronics. It's full of neutron stars and iron layer in this outer crust and the electrons, and the inner crust should be some nuclei, electrons, and the neutrons. Maybe there is some protons with the more and the liquid rotating inside the neutron star, and oppositely to the electrons. And the density of the star decreasing as we goes deeper, and so as we say that this part in the quark hadron transition and the quark model part, it is core part is still unclear, and it purely depend on nuclear models of the neutron star. So here, simply a demonstration is shown that how the lever consists of neutron stars, and I will go to here the degeneracy effects of gravity and the matter in neutron stars. So what does it mean? Yeah, in the inner space, there is a space-time solution for interior solution for neutron stars. For space-time, we can search the space-time in this form, but here the mass function is depend on the matter and the gravity. So, for example, here I show the Einstein field equation, so which is responsible to the space-time curvature, and in the right-hand side we show we see the matter of the star. It is reasonable because more denser, which can influence on the space-time, and so this P and the rho and the P are density, mass density, and the pressure of the interior of the star. It is purely model dependent. In different models has different dependence of their on the binding energy of the star matter. For example, binding energy particles or nuclei. So some models, so Kretschmann scalar for the neutron for the space-time interior to the neutron star has two. Actually, it is not two; it is three component. This space-time Kretschmann scalar for which comes from matter and gravity, and there is some coupling part of the Kretschmann scalar, which is here the matter, and the energy is coupled, and the first term is Kretschmann scalar for the depending on the nuclear model, and this P and the rho are purely model dependent. From this point of view, this neutron star interior, we can test different gravity models and different nuclear models in interior to neutron star, which are showing the same effects on the space-time. So this is, in this point of view, matter and gravity mimics each other, or if we can work on some exact neutron star, so nuclear matter and gravity model, we can get some constraints on these two their parameters, where these parameters show similar effects or the same effects. This is in this study point. This is from our group, Faruk Fatayip, working hard on it, on this field, and I think we can also try to explore this field, which is very interesting from astrophysical point of view. So, magnetosphere of neutron stars. So this is magnetosphere of neutron stars is depend on the outer solution of gravitational field effects, exterior solution of gravitational field effect. For the first time, this magnetic field configuration is so Maxwell equation have been solved in Newtonian frame. For rotating dipolar magnetized non-relativistic star, and then in this Ginsberg-Odernoy and Anderson-Cohen has studies for this in the Schwarzschild space-time, which is star which is not rotating, and but neutron star are rotating, we know. So here the some solution is obtained by Muslim Obsidian, and independently this what we can say, this is well explained the solution in the Resul Ahmed Miller in the series of these papers. Actually most results have been obtained here, and the last one is some included some oscillations of the stars. Here I show my results, which is obtained in Johansen-Psalz's solution. It is not exact analytical solution of Einstein field equation or some field equation in modified gravity, but it is parameterized solution, which is it included some small perturbation to the space-time as with the deviation parameter in this for the space-time, and these these studies have been performed in slow rotation approximation, because Kerr does not work in even fast rotating millisecond pulsars, because spin parameter of neutron stars we calculate, this is very small, and the contribution, this square of spin parameter is very small. It is 10 to minus 3. It is a contribution of the spin into the gravitational field. Square of spin, it is very less than very less percentage, and we assume the high magnetic field does not change the space-time around the star, because its effects, even the surface, minus 10 to minus 7 times less for even for magnetars, highly magnetized objects. And our calculation, we show here the magnetic field lines, and we show that this positive values of value of deviation parameter is compress this magnetic field line and brings to increase the magnetic strength of the this radial component. Here we compare all our results with the results which is obtained in the GR limit. And then we also studied in MOG, modified gravity theories, the solution. In this case, we obtained solution in analytically, and we also tested this MOG effects, and we can see that the magnetic field lines at the surface of the star goes to polar capsize. And lines are become more dense. It showed that the surface magnetic fields will increase with in the presence of positive values of MOG parameter. And then magnetosphere, neutron star magnetosphere. So how plasma magnetosphere forms around the neutron star. So if we can easily estimate this electric field which is being parallel to the magnetic field. We can call that this induced electric field, and it is 10 to power 10 volt per centimeter cube per centimeter. So this is a very huge potential difference even in 1 centimeter distance. So electron can increase up to the 10 billion electron volts, 10 giga electron volt in 1 centimeter distance. So this this high electric field can pull out these electrons from the surface of the star, and this star the charges along the magnetic field line creates gamma ray. Gamma ray in turn is produce pairs, positron electron pairs. So these positrons and electrons accelerate in opposite side, and they also create gamma photons. This cascade generation makes plasma magnetosphere around neutron star. So the star, as star rotates, the magnetic field lines are correlated with the star, and as this magnetic field line goes far, their linear velocity of the magnetic field line reaches the speed of light, and here the light cylinder where this lines are closed. This last closed line is speed the same as the speed of light, and the other outside of the star, the magnetic field lines should rotate with speed higher than speed of light. It is not it is unphysically, so we can cut the area with the light cylinder. So as we told about this induced electric field, now we can calculate the scalar potential of the induced electric field using the Poisson equation. So here this is the specific effective charge density, and this is the Goldrich-Julian charge density, which is the source of induced electric field purely, not including this space charge. This is how to calculate. This is a way how to calculate in the frame of Newton gravity, but in general relativistic solution of equation of the Poisson equation. It is quite long, and I'm not going to show details of. And here I am going to talk about the pulsar does. So as pulsar ages, they slows down, and the potential drop. So this electric field cannot be provide such energy for such amount energy for electrons, which can create high energetic gamma quanta, and then gamma quanta should create electron-positron pair. So when the energy of gamma quanta less than the energy of 2 times rest energy of electrons. So this cascade generation cuts and stops, and the plasma magnetospheric radiations of neutron star stops, and this radiation stop, and we cannot see the neutron star from observations. So as the condition defines energy budget deadline. So for the first time, Ruderman and Sutherland suggested, and this energetic condition for the deadline also is quite long, and I provide here some results, which is depend on this deformation of the star, space-time exterior to star, and these results show that this as for positive values of the deviation parameter, this line decrease. So what is the line? Line, if a pulsar lies under the line, so from line mean if a pulsar position lies under the line, this pulsar cannot be visible. So it can be disappeared from observations. So we can observe only pulsars only which are located above the line. So if here we get some constraints on the epsilon parameter, so deviation parameter, assuming that this line lies on the this pulsar position lies on the line, and we get some limites which is using the observational parameters of these 4 pulsars, and the limites for these pulsars in the frame of Mach gravity, as we can see. So Mach parameter also shifts the line up, and the pulsar being visible can disappear from observation due to the presence of Mach field. Mach field is a field which is which has scalar, vector, tensor characteristics, and if we can explain using this time dependence of the, if we can assume this epsilon parameter is time dependent, so this the variation of the time dependent, the epsilon parameter, as it is time dependent, we can construct from here the luminosity of the star as the time dependent, the dependence of the star, the variation frequency of the epsilon is much higher than this pulsar rotation, so we can drop from Maxwell equations, and if epsilon is time dependent, this pulsar line should change the position in the pp dot diagram depending on time. And for example, if this pulsar lies on the line when epsilon decrease, the pulsar becomes under the line and disappears from observation, and after some time it comes back, and we can see again this, and we can suggest this model for the intermittent pulsars, part-time pulsars. There is some models. For the first time, this part-time pulsar observed in 2006. It was observable in 20% of observation time, and on period it lives 5-10 days, and in off period. Off period means we cannot observe in the same place, in the same coordinate of the sky. So distance of the pulsar was to 4.6 kiloparsec from us, and after that the authors of this paper suggested the pulsar should be some reactivated dead pulsar, should be some reactivated dead pulsar, and so there is more models, more approaches to explain this part-time pulsar niche feature, and we suggest it should be some time-dependent deviation parameter can explain the model. And using the design condition for different radiation model is different. For example, there is the curvature radiation model and the radiation using this inverse Compton scattering process. We can get some different condition for the design condition, different relationships for the design conditions. And in this work, we tested this Einstein ether gravity, which has this two parameter, extra parameter, which is responsible for the experiment for the ether field, and we got lower limits for these two parameters using these two radiation mechanisms, and for isolated neutron stars, because this model also works in the for isolated neutron star models. Energetic losses of neutron stars has two. We can divide it by two. So plasma magnetospheric radiations, which comes from this along open field lines, and dipole radiation. So here we show that the dependence of luminosity of magnetospheric radiation on the this compactness parameter, which is the mass to radius ratio, and we can see as compactness parameter increase, this plasma magnetospheric radiation luminosity also increase, and Mach field also cause to increase the radiation. But dipole radiation, we know that it does not depend on mass of the star, and at 0 we can see this is equal to 1, and this is the same as GR, and but in the presence of alpha parameter, it become depend on the mass of the star and mass and the radius of the star. So this shows that in the presence of some external scalar vector scalar tensor fields, so the star around the space-time around the star become depend on the mass to radius relation, and the studies of the luminosity, radiation luminosity in the deformed space-time using the Johansen-Pstalz model show that there is some critical value in the epsilon where the luminosity reach its maximum. So numerical calculations show that this maximum is about the 10 billions time more than typical value. So for spherical value, so we estimated in the Newtonian this luminosity was in previous calculations. We showed that it is 10 to the power 38 ergs per second, and then in the presence of this critical value of the deviation parameter, it increases up to the 10 to the power 47 erg second. This value, the same order with the luminosity of FRBs, fast radio bursts, which is for observed first time in 2007 by Lorimer Duncan, and there is still open questions on this FRBs origin of FRBs, and some FRBs are repeatedly come And when I started my seminars for my defense, I suggested this model, and at the end of the 2020, the paper arrived in Nature, published in Nature, that analyzing this FRB, which is being repeating FRB, they show that this FRB come from some magnetar, originated from magnetar, and it is originated from magnetosphere of the radio emission. And here we also suggested this model should be, if this epsilon is time dependent, we can also explain this FRBs using this energetic properties of the neutron stars. So, as we told about this primary electron accelerators along the magnetic field, and here the two different analyses shown for the gamma Lorentz factor of the stars, and in inverse Compton scattering model say that this, if particle accelerates up to the about 50-60 value, gamma 50-60, and the particle radiate again and loss its energy and comes to the rest position, and then it starts again accelerating due to the external electric field, and this curvature radiation mechanism can explain the not radio emission, but gamma ray and the X-ray emission, which in this case particle reaches up energy up to the Lorentz factor billion times more than the rest energy. And trajectory bound of particles, actually charged particles, can be found using this expression. And what is trajectory bound? And so charged particles cannot escape from this region. This cannot escape this region during following this open field lines, and we study that this presence of alpha parameter, the Mach positive Mach parameter, this wideness of the trajectory bound become very smooth and narrows this, and we can see that the smooth laser-like jet from neutron stars can be observed this in the presence of this Mach parameter. The same results also we can see this positive deviation parameter can make it narrow this laser-like beam. So I think these are repeatedly comes. So I think it is enough. It is all. It is end.